Hello dear students. So in the previous class we were discussing about the boranes and hydrides. So today we'll discuss about the conversion of esters and amides to aldehyde. How can we convert ester or amide to aldehyde? So ester directly converting to aldehyde and amide directly converting to aldehyde. And here we have already discussed how the esters could be converted to ester could be converted to alcohol. We have discussed it. So I have asked you to write down the mechanism, and if you have written the mechanism, you would have seen that there is the formation of a species like this. Once the ester is treated with lithium aluminum hydride, you are going to get a species like this. Here, if the if the bonds are broken like as expected in the previous mechanism, you are going to get actually an aldehyde. But lithium aluminum hydride, as we have discussed in the previous class, it will not stop in one step. It can provide many more hydrides, like minimum 4 hydrides could be delivered during the course of the reaction. So aldehyde will not be the terminal step of the reaction. It will again get reduced to give alcohol. So the reason is the aldehyde is bound to get reduced to alcohol. So it's not easy to prepare aldehyde directly from ester. And generally what do we do is, this is a medicinally very important compound, and this aldehyde is required for the synthesis of an antibiotic that is called monensin. And how do we prepare this monensin, if you ask? What do we do? We take this ester, it is readily available, and we'll make it completely reduced to give alcohol, and this alcohol is again oxidized to get aldehyde. That's how we used to do. But there is a reagent. By using this particular reagent, what can you do, if you ask? You can directly convert this ester to aldehyde. Means instead of going for a complete reduction, you can stop the reduction somewhere on the way so that you will get aldehyde. So what could be the requirement for the reagent what you are going to use, so that you will get aldehyde instead of getting alcohol? So if you keenly observe these reactions, you could see that what matters is, it is the number of hydrides you provide. In this lithium aluminum hydride, there are many hydrides available. You can restrict the number of hydrides into single one. So if you restrict the number of hydrides into single hydrides, definitely you are going to get aldehyde from ester. So there is a reagent like that. That reagent is what we call diisobutyl aluminum hydride. And this diisobutyl aluminum hydride is again called as DIBAL. It's the abbreviation actually, or even call it as DIBAL like this, just DIBAL. This is what the structure of diisobutyl aluminum hydride. So you would have heard of silane, borane, just like that. It's an alane, means this is silane is SiH4, borane is BH3, alane is AlH3. So this AlH3 is derivatized to give diisobutyl allyne. So you could see that from this diagram itself, there is only one hydrogen available. So this hydrogen is available as in the form of hydrate because it is attached to aluminium. Aluminium is electropositive, so generous to donate the pair of electrons. So it's an allyne, and they do exist in the form of dimers, bridged dimer, that's how it is. You can recall the structure of diborane, that's how it appears. And one more interesting factor about this, the silane, that is diisobutyl aluminium hydrate, is this by itself, by its own, it's not a reducing agent. It cannot release hydrogen or hydride. So how does it happen? This dibol will react with the ester, and there will be the formation of a Lewis acid base complex. Lewis acid means you can recall the substance which require electrons are called Lewis acid, and the ester is electron rich, and it will be donating a pair of electron to aluminium. There is the formation of a Lewis acid base complex, that is this is the Lewis acid base complex, and this Lewis acid base complex is formed. Then what will happen? This aluminium will be ready to donate a hydrogen with a pair of electrons, and that time, once the Lewis acid base complex is formed, this aluminium the diisobutyl aluminium hydrate will act as a reducing agent, and now what happens is this hydrate will be transferred to this carbonyl carbon, and this oxygen will acquire a pair of electron, and there will be the formation of a tetrahedral complex like this. And this tetrahedral complex will be broken when you work out with some aqueous solution. Only in aqueous workup it collapses to aldehyde, so you get an aldehyde like this. So here, what drives the reaction, the scope of the reaction, if you ask, it is the only hydrate which is available with diisobutyl aluminium isopropyl, that is dibol, and once this hydrate is transferred, the reaction stops. If one more hydrate would have been available, then it will be leading to the formation of alcohol. That's what the importance of diisobutyl aluminium hydrate. It's one of the synthetic reagent you are supposed to learn actually. So hope you understood what is the importance of this diisobutyl aluminium isopropyl diisobutyl aluminium hydrate. And interestingly, this reduction will happen even at minus 70 degrees Celsius, and the yield of the reaction is found to be 88%. Wow, it's a wonderful yield. Interestingly, even dibol could be utilized for the reduction of nitriles to aldehyde. So here you get aldehyde. So you could see that this part has become aldehyde. For this, dibol is utilized. And here also the availability of one single hydrogen that makes the purpose done. The conversion of nitrile to aldehyde. So how do we convert amides to aldehyde? So amides to aldehyde, it's in the previous class we have seen how amide could be converted to alcohol, and the reagent what we have used is lithium aluminium hydride. And during the course of the reaction, you have seen a tetrahedral intermediate. So if you recall in the previous class that this will get collapsed to iminium ion, and there is a condition for the collapse of this tetrahedral complex to iminium ion. What is that condition? It required a high temperature to promote the collapse of this tetrahedral complex to iminium. So the strategy, what do we do? We'll reduce the temperature as much as possible. So here we are conducting it at 0 degree Celsius. So in aqueous solution at 0 degree Celsius, this will not get converted to iminium ion. It will give an aldehyde. That's what the strategy. So here we are not using any particular reagent or anything. So we just reduce the temperature. Instead of giving alcohol, we will get the aldehyde. That's the strategy. Here you could see the summary of all this reduction reactions of the carbonyl group. See, we were discussing about the lithium aluminum hydride. Lithium aluminum hydride can reduce the esters very slowly. See that lithium aluminum here, it reduces very, not lithium, I'm sorry. Sodium borohydride can reduce esters very slowly. Lithium aluminum hydride is very strong reducing agent, and it works on the principle of electrophilicity of carbonyl group, and whereas BH3 it works on the principle of the electron richness. So here things happens very fast, because if you take amide and carboxylic acid, their carbonyl group, it is electron rich. See here, in case of lithium aluminum hydride, carboxylic acid will not be reacted. Why it is not reacted? The electrophilicity of carboxylic acid is, the carbonyl group of the carboxylic acid. Electrophilicity means it's not electrophilic, this part. It's electron rich because of this pair of electrons are involved. So like that, you can see this this chart and have your own analyze, so that you will get a better understanding. So what reagent could be used for the reduction of various carbonyl groups, and what are the products, everything is written. So the point is, like, borane works in a different mode and boron hydride work in a different mode. So this part is very important. Hope you understood. So till now we were discussing about the reduction of carbonyl groups into maximum alcohols. So RCHO gives RCH2OH. Actually, is it the final product of the reduction? No, actually it can be further reduced into RCH3, or it could be told like this: RCHO converting to RCH3. This is the final product. So let's see how could we convert the RCOH to RCH3. Actually, this could be also read like getting rid of the functional group. So here the carbonyl group is getting converted to CH2 group. So how could it be done? So there are many methods for converting this CO group to CH2. Out of that, two methods are very popular. The very first method, it is Clemmensen's reduction. In Clemmensen's reduction, zinc amalgam in presence of HCl will be used, so that you get the CO will get converted to CH2. Of course, it has to be in aqueous HCl. And another method is, you can go for treating with hydrazine hydrate, that is NH2, and in presence of a base, generally potassium hydroxide or sodium hydroxide. So this will convert RCOH to NaOH. The main difference is like this Clemenson's reduction is easier comparing to Wolff-Kishner reduction. This is what we call Wolff-Kishner reduction. Wolff-Kishner reduction. This is called Clemenson's reduction. Tell me, what are the difference between Clemenson's reduction and Wolff-Kishner reduction? The main difference is Clemenson's reduction is happening in acid, whereas the Wolff-Kishner reduction happens in basic medium. Both of them are complementary to each other. Both of them does the same job. And Clemenson's reduction, it is easy to perform, but it fails. It may fail for some acid sensitive aldehydes and ketones, and also it is not applicable for the aldehydes which is having high molecular weight. And if you take the Clemenson's reduction, ketones has got a good inclination towards Clemenson's reduction than aldehyde. And Wolff-Kishner reduction, it's been modified by you can replace this this hydrazine hydrate and base. Both could be replaced by a single substance, that is dimethyl, this is another modification. You can modify it by using diethylene glycerol. If you use this diethylene glycerol, it is called Huang-Millen modification. It is there in the syllabus. This Huang-Millen modification, it's nothing but the Wolff-Kishner reduction. Instead of using hydrazine hydrate in presence of a base, we have used diethylene glycerol. That's the difference, nothing more. Actually, this Wolff-Kishner reduction is again modified. There is dimethyl sulfoxide and potassium tertiary butoxide. You can even use dimethyl sulfoxide, also potassium tertiary butoxide. This is another modification for Wolff-Kishner reduction. And if you are using this trimethyl sulfoxide, the advantage is it could be even done at room temperature. So this is a moderate condition for Wolff-Kishner reduction. For the Clemenson's reduction, the condition could be made a bit more strong by using the method could be modified by using activated zinc and gaseous HCl in presence of organic solvent. So basically these are the two reactions, very popular reactions, that will help us to convert CO group to CH2. Few points you have to remember about the Clemenson's reduction and the Wolff-Kishner reductions are: alpha hydroxy ketone won't give the Clemenson's reduction or Wolff-Kishner reduction. They give ketones or olefins. The same way 1,3-diones, they won't give the expected product, they'll be giving a rearranged products. And alpha beta unsaturated ketone, if you go by Wolff-Kishner method, you get pyrazolines. If you go by Clemenson's, you get olefins. The sterically hindered aldehydes and ketones will not go for Clemenson's reduction, or neither Clemenson's reduction nor the the Wolff-Kishner reduction. And pinacols mostly give many side products. These points you have to remember. If you look at the mechanism, especially in Wolff-Kishner reduction, we know that it is hydrazine in presence of NaOH. So how does it happen? How the reduction of carbonyl group to CH2 group happens, if you ask? From hydrazine, nitrogen is having a great tendency to get liberated from hydrazine. During the course of the liberation of nitrogen, what happens? The aldehydes or ketones get reduced to CH2 group. The mechanism is little complex actually. So here first the aldehydes or ketone will get reacted with hydrazine to form hydrazone, hot concentrated sodium hydroxide solution deprotonate the hydrazone. So what happens? This deprotonation happens. This bond will come over here, so that you will be getting. So what happens? This nitrogen will become electron rich, so it will have a tendency to delocalize the electron density. So what happens? This CN bond will absorb a proton from aqueous solution, so it gives a compound like this, and this compound is little acidic. So what happens is, in the hot concentrated solution, this proton will be absorbed, and the absorption of that proton will show a way for these two nitrogen atoms to escape from the molecule in the form of nitrogen molecule. So simultaneously what happens? One of the proton will be absorbed. So when it goes, this bond will absorb a proton. So it will be automatically nitrogen. It will fly away. It will get liberated. Along with that, there will be the formation of the so-called alkane. And there is no actually here it is supposed to be the formation of an alkyl anion, and immediately what will happen? It will absorb a hydrogen from a proton from water molecule. You know that alkyl anion is highly basic. This is how the reduction of carbonyl group happens to alkyl group through hydrazine hydrate and concentrated basic solution. Actually, the Clemmensen has got the most complicated mechanism, even though it is very easy to perform, as I have told earlier. It has got most complicated mechanism. And how does it happens, if you ask? When the zinc is dissolving, in concentrated HCl, it gives zinc ion and 2 electron. When these 2 electrons are having nothing to do, it will react with the H plus ion in the aqueous solution, and it will give H2. Same time, this H plus are actually combined with the Cl minus, and 2 Cl minus will combine with Zn2 plus, and there will be the formation of zinc chloride and H2. Zinc chloride and H2 will be formed, but in the presence of carbonyl compounds, if nothing else, there is nothing else actually, this hydrogen will be reduced to hydrogen, but there is the presence of carbonyl group. What will happen? This electron will go to carbonyl group, and it will reduce the CO bond to CH2. That's how they say. Actually, this Clemenson's reduction is a part of metal dissolving reduction, which we are supposed to discuss soon.